Hi everyone, welcome back to Vijay Datta chemistry classes. This is Purnima ma'am. In the previous class, we have started states of matter and gas laws, three, four gas laws, that is Boyle's law, Charles' law, Avogadro's law. These laws, Gay-Lussac's law, these laws we have discussed, and also we started the ideal gas equation, right? So today I am going to continue with that class. Ideal gas equation. What is ideal gas equation? Already in the last class also we have derived that PV equals to nRT, where P is the pressure, V is the volume, P means pressure, V volume, N is nothing but number of moles. Already we know that formula for number of moles is N equal to given weight by number of moles is nothing but given weight by gram molecular weight. Gram molecular weight, this is called number of moles. Okay, gram molecular weight. R is called ideal gas equation. R is the ideal gas constant or universal gas constant, like we can say it is ideal gas constant or universal gas constant. And T is the temperature. This temperature already we have discussed, we should convert into the kelvins. If they given 0 degrees Celsius, that one you have to add 273 Kelvin and you have to convert into 273 kelvins. Degrees Celsius, whatever the problem is given, you have to convert into the kelvins. Now come to the R value. R value changes when the value, when the units of pressure and volume is changing, R value will be changes. Understand? See, pressure if you are taking in atmospheres, volume you are taking in liters, then in liter atmospheres R value will be vary. Otherwise, R you are taking in bar or tar, volume you are taking in milliliters, like that. So the value of R will be changes. So here for R we have a different values. So let us see the numerical values of R. Some numerical values of R. Numerical values of R. See here, generally what is the relation we have? PV equals to nRT, where n equal to 1 mole. If I take when n equal to 1 mole, then the relation becomes PV equal to RT. Then we want to calculate R value. Then R equal to PV by T. P is the pressure, T is the temperature, V is the volume, we know that. So here we are taking the STP conditions. At STP conditions, that is nothing but for 1 gram mole, for 1 gram mole of a gas, yet 1 atmosphere, pressure is 1 atmosphere, and volume is 22.4 liters, and temperature we are maintaining 0 degrees Celsius, that is I am converting into the Kelvin, so it will be 273 Kelvin. If you substitute these pressure, volume and temperature values in the R, then you will get R value. R equal to 1 atmosphere into 22.4 liters by 273 Kelvin. You will get 0.0821 liter atmosphere per Kelvin inverse and mole inverse. Why mole inverse? Because n equal to mole. We are writing that actually PV by NT, right? N is the mole, T is the temperature. When n equal to 1 mole we are taking. So its units will be 0.0821 liter atmosphere per. If you are writing, then no need to write the inverse ma. If you are not writing the per, then you have to write the inverse. Okay, this is the one type of value for the R. And see, if say this is the case 1, this is case 2, already it is the case 1, then what is in the second case? If you are taking pressure in dyne centimeter square, dyne per centimeter square, and volume you are taking in milliliters, then pressure equal to 76 is the mm of Hg, right? So that 76 into 13.67 into 981 dyne centimeter square. So that mm of Hg we converted completely into the dyne per centimeters square. Then volume we are taken in ml, actually 22.4 liters. If you are converting into milliliters, it becomes 22,400 ml. The temperature as usual we'll consider it is for the 273 kelvins only. Then you want to R value, then substitute all these values, 76 into 13.67 into 981 into 22,400 PV by N, 1 mole, temperature is 273. If you calculate this value, you will get 8.314 into 10 to the power of 7 erg Kelvin inverse mole inverse. So here R value is 8.314 10 to the power of 7 when you have taken in the ergs, means dyne per centimeter square is the erg value. Okay, already we know the relation, that is 1 joule. 1 joule equal to 10 to the power of 7 ergs. 1 joule equal to 10 to the power of 7 ergs. Then if you convert R value into joules, then R equal to 8.314 into 10 to the power of 7 ergs. In this place we can write joule. So 8.314 joule Kelvin inverse mole inverse. So R value, one more R value, 8.314 joule Kelvin inverse mole inverse, 0.0821 liter atmosphere, and 8.314 into 10 to the power of 7 Kelvin inverse mole inverse. These are the different values. You can take R value even in calories also. That is the third case. If you are taking R calories, if you want to calculate the in calories, then 1 calorie is equal to these are the basic values, 4.184 into 10 to the power of 7 erg. erg. Actually, it is a 1 calorie value. 1 calorie in ergs is the 4.184 into 10 to the power of 7 ergs. But already what we know that 8.314 into 10 to the power of 7 erg Kelvin inverse mole inverse. This is the R value we know. But if you want to convert erg into calorie, then 1 erg is equals to 1 by 8.314 into 10 to the power of 7 calories. So I want to substitute that value is here. So 8.314 into 10 to the power of 7. In the erg place I am writing 1 by, sorry, 4.184. 4.184. So 1 by 4.184 into 10 to the power of 7 calorie. Kelvin inverse, mole inverse. If you calculate this value, 10 to the power of 7, 10 to the power of 7 get cancelled. 1.987 calories per Kelvin mole we'll get. 1.987 will be round figure as the 2. So R value in calories is 2. Generally we'll apply R value in calories is 2. So here for R we have seen total 4 values. The case 1 is 0.0821, 8.314 joules, 8.314 into 10 to the power of 7 or Kelvin inverse mole inverse, and R value 2 calories per Kelvin in calories if we are considering, right? Okay, these are the numerical values of R. Okay, now we have an idea about the ideal gas equation also. Now one more thing here, calculating the density also, density calculations also we have. Actually what is the ideal gas equation? We have PV equals to nRT, right? So PV equal to N is nothing but given weight by molecular weight, that already we know that number of moles formula is weight by molecular weight. If this volume comes this side and molecular weight comes this side, then Pm equal to W by V into RT. See, Pm equal to weight by volume is called density. So I am introducing the word D because D is equal to, means density is equal to weight by volume is called density. And here number of moles equal to weight by molecular weight is the number of moles. So I want to calculate density, then the formula is Pm by RT. D equal to Pm by RT. This is the formula for the density calculations. Not only this, you can alter this formula as, if you want to calculate the temperature, then the value will be Pm by R into D. If you want to calculate the M, if you want to calculate the M, then the value dRT by P. If you want to calculate P, then dRT by M. So these are the formula. However, you want whatever he asks to calculate, you can calculate by using these gas. Okay, right. So this is about the ideal gas equation. Till here, we'll do some exemplar problems in this session. Okay, today's session, some exemplar problems. Exemplar problems on gas laws and ideal gas equation. Okay, okay. Let us see. Comes to the first one. I want to take a sample of a gas. A sample of gas occupies a volume 512 milliliter at 20 degrees Celsius and 74 centimeter of Hg as pressure. What volume would this gas occupy at STP? So this is the question, how to do the problem. A sample of gas occupies a volume 512, means he given the volume he given and the temperature also given, and again here 74 centimeter of Hg means pressure is given, right? So what volume would this occupy at STP? So he given general conditions and we have to find the STP conditions. Okay, what volume we have to find at the STP condition. So initial conditions means what he has given, final conditions means STP conditions. So in the initial, what is the volume he given? 512 ml is the volume. Temperature is 20 degrees Celsius, but this one we have to convert into the kelvins. So I am adding 273, then it is 293 Kelvin. Volume temperature. Now come to the pressure. Pressure is given 74 centimeter of Hg. It is the pressure is given. Yet STP we have to find. Yet STP pressure, suppose these one we are considering as P1, V1, T1 are the initial, then at STP conditions, pressure is in mm of Hg, centimeter of Hg we have to consider, then that is obviously 76 centimeter of Hg. The value is fixed, right? If you want to take mm of Hg, 760 will be its value. Then temperature, already we have taken these STP conditions, then temperature at STP conditions is 273 Kelvin, means we will consider 0 degrees Celsius, but we will add 273, then it becomes 273 Kelvin. Then he is asking to calculate the volume. So already we know the relation, that is we have P1 V1 T1 and P2 T2 V2. V2 we have to calculate, then we have a formula, that is P1 V1 by T1. This is according to the ideal gas equation only. PV equal to RT. R is the constant, then it is PV by T. R is the constant, right? So we can take it for two different gases. P1 V1 by T1 equal to P2 V2 by T2. So this is the formula. Okay, this is the formula. Now we are going to apply. What is the P1 value? P1 pressure he given 74, right? So 74 into volume he given in milliliters, that is 512 by temperature is 273 and 20 we added, so the value of temperature is 293, which is equal to pressure we have taken 76, volume we have to find, by temperature is 273. If you calculate all these values, we will get the V2 value. Okay. So the V2 value, how much you are getting, you can calculate and we can find. So 74 into 512 into 273 by 293 into 76. So if you calculate this, you will get the answer. That is in milliliters only, you will get the answer. Okay. So this is one type of problem, exemplar problem. And one more problem also there, that is which is very very important. I'll go to the second one. First problem is easy only, comes to the second one. The density of a gas, the density of a gas is 0.259 grams liter inverse at 400 Kelvin, at 400 Kelvin and 190 torr pressure, that pressure is given. Find its molar mass. Find its molar mass. Okay. So first of all, we'll write what is the data is given. See here, density of a gas, density is given, that is 0.259 grams per liter. Then he given the temperature. Temperature is given in Kelvin only, so no need to change. That is 400 Kelvin. Torr means pressure is given, and 190 torr. Right. So this torr, it is in liters. It is in Kelvin. So we have to go for the formula. What is the formula? P equal to. We want to calculate the molar mass, right? So in the previous session, the previous one, here we want to calculate the molar mass. Then what is the formula? Density RT by P. So dRT by P, same formula I am applying here. That is density, molecular mass equal to dRT by P. But to consider the R value, we have to maintain the uniform units. That is a liter. If it is in liters, then pressure should be in atmospheres. So we have to convert the atmospheres, tar into the atmospheres. To convert tar into atmosphere, 190 by 760. Tar by 760 mm of Hg will gives you the atmosphere. So to convert torrs into atmospheres, we have to divide with the 760. Then the conversion will be like this. Okay. Now, what is the R value? R is in liter atmosphere. When it is in liter atmosphere, 0.0821 liter atmosphere per Kelvin mole. It is R value. So now we have all the values. Just if you substitute, we can get. That is 0.259 into 0.0821 into temperature is 400 Kelvin by pressure is 190 by 760. If you calculate this, you will get the answer. Right. So you calculate and you will write the answer. The answer is 0.259. No, anyway, this 760 also comes up. Then denominator one comes to the numerator. Then calculate and find the value. Okay, guys. So this is the one more problem. We'll go to the another problem. We'll see the some different problems. Next problem is, what percentage of a sample, what percentage of a sample of nitrogen, sample of nitrogen must be allowed, must be allowed, must be allowed to escape if its temperature, if its temperature, pressure and volume are changed from, are changed from 220 degrees Celsius, 3.0 atmosphere and 1.65 liters to 1110 degrees Celsius, 0.7 atmosphere, and 1 liter respectively. So he is asking to calculate the percentage of sample of nitrogen escaping. Okay, allowed to escape. Right. Now, first of all, we'll go to the initial data. Okay, means before escaping and after escaping. Before escaping, before, and it is the after escaping. Before escaping, what are the pressure? 3 atmosphere, volume is 1.65 liters, temperature is 220 degrees Celsius. This one you have to convert into Kelvin, then it will be 4 493 Kelvin. Right. Now comes to after escape. Before escaping of nitrogen gas, it is after escape of nitrogen gas. He given the conditions, that is pressure is 0.7 atmosphere and volume is 1 liter, then temperature is 1110 0 degrees Celsius. That one I am converting into the Kelvin. Then 383 kelvins. So these are the before. First, what we have to do, mass of a gas. First, we have to find the mass individually. Mass of a gas before escaping, mass of nitrogen gas before escaping, mass of nitrogen gas after escaping. Then, if we get the difference between the masses, then we'll get the percentage of nitrogen. Got it? So first, here I am going to use the formula, that is PV equal to nRT only. Already we know N is nothing but weight, means mass by molecular weight. Then PV equal to weight by molecular weight into RT. Here we want to calculate weight. Then PVM by RT. This is the formula I am going to use. First I am calculating the mass before escaping condition. Before escaping, W means mass equal to pressure is given. How much the pressure is given before conditions? 3.0, means 3.0 into volume. How much they have given? Volume is 1.65 liters. So 1.65 into, we want molecular weight, right? Molecular weight of nitrogen we know, that is 28, by R value, liter atmosphere only, no, 0.0821 into temperature. What is the temperature? 493, right? So 493. If you calculate, this is before N2 escaping, before a gas escaping this one. If you calculate this one, you will get the value 3.42 grams, right? Okay, 3.42 grams. Now come to the after conditions. Same formula. What is the pressure after conditions? Pressure is 0.7 atmospheres. So pressure is 0.7 atmospheres. Volume is 1 liter. Molecular weight of N2 is obviously 28 only. It is also liter atmosphere, so R value also 0.0821 into, what is the temperature after conditions? 383 Kelvin, right? If you calculate this one, you will get the value 0.62 grams. So it is the nitrogen before escaping, mass of nitrogen. It is after escaping, mass of nitrogen. If we get the difference, how much amount of the mass we can calculate, right? So percentage, first we'll get the mass of the nitrogen, difference in the mass of nitrogen. Then 3.42 before minus after, 3.42 into 0.62, right? So 0, then 14, 6, then 8, then 2. So 2.80 is the difference, isn't it? So this 2.80 grams, we have to, he is asked a percentage of nitrogen allowed to escape, not the mass of nitrogen. So to calculate the percentage of nitrogen to escape, 2.80 by total mass of nitrogen is how much? 3.42 grams into 100. then simply we'll get the percentage, that is 81.87 percentage of nitrogen is allowed to escape. Simple calculation, before and after conditions we find, then we have to calculate percentage of nitrogen, how much it was escaped. That percentage calculation is nothing but the difference in their mass by total mass into 100 will gives you the percentage of nitrogen, guys. Okay. uh, so this is about the some problems on the gas laws and the ideal gas equation. Okay guys, so in my next video I'll come with the Graham's law of diffusion and Dalton's law of partial pressure according to the CBSE. In the textbook we don't have Graham's law of diffusion, but maybe it will be important to the mains point of view also. So in our next class we'll see the Graham's law of diffusion and Dalton's law of partial pressures. Okay. Okay, guys, thank you. Thank you so much.